Hello and welcome to Lecture 9. The data structures we have seen so far were simple data structures like arrays, where each element was accessed using the index or its relative position in the data structure. In this lecture, I will introduce four new data structures that use pointers instead to keep track of elements. These data structures are stacks, queues, linked lists, and rooted trees. This lecture corresponds to Chapter 10 of your reference book. Before we begin, let us first look back and recall what was covered in the preceding lecture. The previous lecture covered sorting algorithms that ran in linear time under certain assumptions. Unlike comparison sorts, these algorithms do not perform comparison tests to sort the input. The first linear time sorting algorithm was the counting sort. To run in linear time, it assumes that the n input elements are integer values within some range between 0 and some integer k, where k is less than or equal to n. It does not sort in place, but is stable. That is, the relative order of elements with the same key value is maintained in the sorted output. Next, we saw the radix sort, which is a stable sorting algorithm and sorts the d-digit numbers or d-character words column-wise starting from right to left. It assumes that d is bounded by k to ensure a linear running time complexity. Finally, we saw the bucket sort, which assumes that the input sequence is drawn from a uniform distribution to ensure that the buckets are filled more or less equally. This assumption is very important as it uses insertion sort to sort the elements in each bucket. If this assumption is not made, then we may end up with large number of elements listed in some buckets, thus making insertion sort inefficient as it does not perform well for large number of inputs. Since it uses the bucket array, it is not in place, but is stable as it uses linked lists in each bucket. The data structures we will be studying today are dynamic in nature, as their sizes changes based on the pointer values. Remember that the arrays we have seen so far were static data structures, where we needed to know the size in advance and could not modify it during the execution of the algorithms. The delete operation on stacks and queues are very easy to understand. In a stack, when we delete an element, we always delete the topmost element on the stack. Therefore, the discipline followed in a stack is first in, last out, or FILO, or equivalently, last in, first out, LIFO. In classical queues, however, the element is always deleted from the head of the queue. That is, the element that has been waiting in the queue the longest is removed first. So the policy followed by queues is first in, first out, or FIFO. Before we begin with the details on how stacks work, let us take a look at a very simple example and understand the basic operations that can be applied on stacks. So for example, a stack can be considered as a pile of plates that you normally see in restaurants. So the first plate that you put, let's call it 1, you push it on the stack. So the first plate will always be the plate that is on the bottom and sits on the table. Then if you put another plate, let's say 2, it goes and sits on top of the first plate. Then we have 3 and 4 and 5 and let's say 7. So now over here we see that we have a pointer that points to the topmost plate or topmost element on the stack. So whenever we want to delete an element, we call pop, which always removes the topmost element on the stack. So if I click pop, it would remove the topmost element. If I click pop again, it will remove element 5, and it goes down. The last operation is the peek operation, which always returns the value of the topmost element in the stack. So when I say peek, it would return the element of value 4, which is the topmost element on the stack. Therefore, inserting a new element on a stack is called push, and deleting an element is called pop. Remember that pop always removes the topmost element referenced by the s.top pointer. If we use an array to represent a stack, we can say that s of 1 will be the bottommost element, that is the element that was first put on the stack, and s of s.top refers to the most recent element placed on the top of the stack. When s.top is equal to 0, the stack is said to be empty. So the push procedure takes the key value x of an element to be placed on the stack and increases the s.top pointer by 1. The pop procedure, however, returns the element on the top of the stack and decrements the s.top pointer by 1. If there are no elements in the stack, that means s.top is equal to 0, then it would return the error stating underflow. The stack empty procedure simply checks if the stack is empty or not and returns the corresponding Boolean value. I have not included the pseudocode for peek. Try to write it yourself. It is very easy. In this example, we have a stack shown as an array with 4 elements already pushed onto it. The first element is 15, and the topmost element is pointed by the s.top pointer, which is 9 and is located at position 4. When we call push s17, first we increment the pointer by 1 and then place 17 to the top of the stack, that is at position 5. Similarly, push s3 increases s.top by 1 and then adds 3. Upon pop, the pointer is reduced by 1 in this example, now pointing at position 5. If we try to pop an empty stack, we get the underflow error. Similarly, when we try to push an element onto a stack that is full, we get the overflow error. Try to include the check for overflow in the push procedure shown on the previous slide. None of the procedures involve loops and thus have a constant running time of O1. In queues, we call the insert operation as enqueue and the delete as dequeue. We use 2 pointers here to indicate the head and tail of the queue. When we enqueue a new element, it is placed at the tail of the queue, just like normal queues that you see at KFC. When we dequeue, we remove from the head of the queue. In reality, the person standing longest in the queue is the one at the head and thus is served and removed first. We can implement a finite queue of size n-1 elements using an array of size n. We will see why n-1 and not n next. To implement a queue, we need 2 pointers instead. One pointer to point to the head or first element in the queue, which we denote by queue.head, and another to indicate the end of the queue called queue.tail. So whenever a new element is added to the queue, we change queue.tail only. And whenever the first element in the queue is removed, we change queue.head. The elements in a queue are therefore placed in positions queue.head, queue.head plus 1, up till queue.tail minus 1. A queue can be circular such that the last position, say n, is followed by the first position in the array. You may ask, why is the last element in the queue at location queue.tail minus 1 and not at queue.tail? The answer is because we need to be able to distinguish between when the queue is empty and when full. When q.head is equal to q.tail, the queue is empty. And when q.head is equal to q.tail plus 1, the queue is full. If we try to add a new element in this case, it would result in an overflow. Assuming that array Q is of length n, the pseudocode for NQ and DQ are given as shown. Again, since there are no loops or iterations involved, they both have a constant running time. Also, the maximum number of elements that can be queued in array Q is n minus 1 and not n. The remaining one empty position is used to check the extreme cases, that is, whether the queue is empty or full. Let's look at an example where q.length is equal to 12, and after some NQ and DQ operation, q.head is pointing at position 7, and the pointer q.tail is positioned at 12. So currently, there are 5 elements in the queue. If we perform the first NQ operation to add 17, 17 will first be placed at position 12, referenced by qtail before it being incremented by 1. Considering a circular queue, qtail will now be pointing at location 1. The next NQ operation puts 3 at location 1 and increases qtail to 2. The third NQ operation puts 5 in location 2 and increments q.tail to 3. When we dequeue, the q.head simply increases by 1 and access to 15 is lost as it is no more at the head of the queue. The next data structure is a linked list and its variants, where the elements are arranged in a linear order. Unlike arrays, the elements in a linked list are supplemented with pointers pointing to other elements. Let us focus on what is called a doubly linked list, where each element is composed of 2 pointers, namely next and. Apart from these 2 pointers, we also keep track of the attribute, which is the key value. So if we are given some element x in the list, x.next points to the next immediate element in the list or the successor, and x.previous points to the previous element or predecessor. It is easy to see that if x.prev is equal to nil, it means that x is the first element in the list. Similarly, x will be the last element if it has no successor, that is x.next is equal to nil. Apart from the prev and next pointers, we also need a pointer to point to the first element in the list. This is the l.head pointer. If the list is empty, then l.head would be equal to nil. I have already introduced one type of linked list to you, the doubly linked list, which looks like the figure given here. Another form is the singly linked list, where each element only includes the next pointer. Therefore, without the previous pointer, the list can only be traversed in one direction, that is from the head to the tail. A list can be sorted or unsorted as well. Like queues, lists can also be circular with the last element pointing to the first element instead of nil. Take a look at this doubly linked list example. The insert operation adds the key 25 to the head of the list L and changes the next and previous pointers accordingly. The delete operation removes the key 4. To do so, it is obvious that the list should be searched first to find the key before deletion. So we need a procedure to search the list L for some key K. This is done by the list search procedure seen here. It finds the first element with key value of K and returns the pointer to it. If K is not in the list, it returns nil. Since a list can have n elements, the running time is theta n, as it may have to search the entire list in the worst case. If we want to insert an element into the list, we use the list insert procedure given here. As seen in the previous example, it positions the element with key k at the head of the list. The procedure only involves updating the pointers and therefore has a constant running time. To remove an element from the list, we use the list delete procedure as given here. As mentioned earlier, to delete a given key, we need to first search the list to find the key. So we need to call the list search procedure that we have seen earlier. Therefore, it requires theta n amount of time in the worst case because we need to do the search operation before deletion. The last data structure that we will be studying today is what is well known as rooted trees. To understand what it is, let us first recall what a binary tree is. For a given binary tree T, each node has three attributes: the parent, the left child, and the right child. To keep track of these attributes for any node X, we use x.p to denote the parent of X, x.left to denote the left child, and x.right to denote the right child. Since it is a binary tree, each node can have at most two children. It is easy to see that if x.p is equal to nil, then x has no parent and is therefore the root of the binary tree. If x.left is equal to nil, then node x has no left child. Likewise, the same holds for x.right. To point to the tree itself, we need an additional pointer t.root, which points to the root node. If this is nil, then it means that the tree T is empty. We can now generalize the concept of binary tree to any generic tree with at most k children instead of just 2. The binary tree representation with each node carrying 3 pointers is shown here. To generalize it, we can have k number of children instead of just 2. But the problem arises when we do not know in advance the bound on the number of children. In such cases, allocating memory space for the tree representation would be impossible. The solution here is to come up with a more smarter representation for trees having arbitrary number of children. What we will be looking at now is called the left child, right sibling representation that interestingly uses only big O n amount of space to represent n nodes. The trick is that instead of having a pointer to each child node, just keep track of 2 nodes. Use x.leftChild to point to the leftmost child of x. Then use x.right sibling to point to the sibling of x positioned to its right. Doing so, we can denote node x with no child as x.leftChild is equal to nil, and the rightmost child of node x as x.right sibling is equal to nil. Therefore, the modified and improved representation of the tree would look something like this, where each node keeps track of its leftmost child and its immediate sibling to the right. In this way, every node can have dynamic number of children.